Energy in simple harmonic motion. Before working through this video, you must know the equations for simple harmonic motion. If you do not, you should refer to the following video, which covers this topic. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. We have already known that in an ideal system with no friction or other non-conservative forces, the total energy is conserved. For example, a simple pendulum converts between gravitational potential energy and kinetic energy, and a mass on a spring converts elastic potential energy to kinetic energy, and vice versa. Therefore, during simple harmonic motion, there is a constant interchange of energy between two forms, potential and kinetic. We know that the kinetic energy of an object of mass m moving at velocity v is given by. We also know that the equation for the velocity of the object at displacement x is. Combining these equations gives the kinetic energy at displacement x. Pay attention. Kinetic energy as a function of position in simple harmonic motion, and the graph below illustrates this. The parabola represents the kinetic energy of an object in simple harmonic motion. Conservation of energy provides a simple method of finding an expression for the potential energy of an object undergoing simple harmonic motion as a function of position. The total energy is the sum of the kinetic energy and the potential energy. The total energy must be constant and equals to maximum kinetic energy. We can rewrite the total energy as total energy is equal to kinetic energy plus potential energy. The potential energy at any position will be the difference between the total energy and the kinetic energy. The graph below shows the variation of potential energy with the displacement. The graph shows that at the extremes of the motion, the system has potential energy only, and in the equilibrium point, the potential energy is zero. The following graph shows energy as a function of position in simple harmonic motion. The variation of the potential energy and kinetic energy with displacement are both parabolas. The yellow line shows the total energy, the red the kinetic energy, and the blue the potential energy. At any position, the total energy is the sum of the kinetic energy and the potential energy, as we would expect. The horizontal line shows the total energy of the system, which is constant. In addition to looking at the variation of energy with displacement, we should consider the variation of energy with time. Again, let us start with the kinetic energy. The velocity varies with time according to the equation. Replacing v with equation for velocity, the kinetic energy is given as follows. The graph of kinetic energy as a function of time looks like this. The potential energy will be the difference between the total energy and the kinetic energy. Take the most important trigonometric identity and rearrange the terms. The graph of kinetic energy as a function of time looks like this. Pay attention in the question. The total energy is equal to the maximum kinetic energy. The maximum speed is found as follows. The amplitude is taken from the graph. From the graph, we take the kinetic energy when x is equal to 2 centimeters. The potential energy is total energy minus kinetic energy. To find the period of the motion, first we calculate the angular speed using the maximum potential energy. We now find the period. Pay attention in this question. It's very important to understand how to find the period from this graph. At t equals 0, the kinetic energy is 0, meaning that the particle is at one extreme of the oscillation. It's 0 again at about 0.17 seconds, when it is at the other end. To find the period, the particle has to return to its original position, and that happens at 0.35 seconds. So the period is 0.35 seconds. To find the amplitude, first calculate the angular frequency. Then use the maximum kinetic energy. We know the displacement, so we use a formula that gives kinetic energy in terms of displacement. Pay attention in this question. The ball will perform simple harmonic oscillations about the equilibrium position because the restoring force is proportional to the displacement. To find the period of oscillation, take the formula for simple pendulum and replace L with R. To plot the graph, we write the equation for velocity. But before, we have to calculate the angular speed. The initial velocity is the minimum velocity, and it is 0. The maximum velocity occurs when the value of sine is 1. We now will find the time when the velocity is maximum and the time when the velocity is minimum, and then we plot the points on the graph.